Today we're going to do 5-1 Part B, which is angle bisectors. First things first, and we might need a reminder of what an angle bisector is. As a reminder, an angle bisector is a ray that cuts an angle into two congruent angles. Actually looking at what that might look like, let's say we have an angle. Let's call it angle A, B, C. If we were to draw the angle bisector of angle ABC, then it's going to be a ray in the interior, in the middle of the angle. But the big key here is that we have the congruent arc marks, meaning that we now have this top angle is congruent to the bottom angle. So we would call that red ray the angle bisector. We've got some theorems in 5-1 that deal with angle bisectors, similar to how we did with perpendicular bisectors. Theorem 5-1-3, the angle bisector theorem, says if a point is on the bisector of an angle, meaning the angle bisector, then it is equidistant, or the same length, from the sides of an angle. So looking at exactly what that means using a diagram, if we have an angle ABC, and according to the theorem we need the bisector of the angle. And so if we were to draw then this bisector, meaning the ray that cuts this angle directly in half, if we choose a point on the bisector of the angle, so you can choose any point on this ray, on this purple line, you can choose any point at all. I'm going to choose a point just about right here. Now, what the theorem tells us is that if you were to drop a perpendicular line down, a perpendicular line, because we're dealing with the length. We're dealing with the length from a point to a line, and we've dealt with that before, and we always said that you're dealing with perpendicular lines. So we have two perpendicular lines, and what our theorem tells us is that these perpendicular lines are congruent to each other. This is what the theorem tells us. And again, you can choose any point on this purple ray. Let's go ahead and prove this theorem. To start this proof, we need given information, and our given information is that PS is the angle bisector of QPR, and that we need to prove that the length of QS is equal to the length of SR. So looking at a diagram, we see we have an angle QPR as our given information told us, but now we need an angle bisector. And so we'll draw a ray to bisect this angle, and we know it is called PS. We've got our diagram drawn, and so let's start with the proof. We always start with our given information, so let's write that down. We've got our given information, so after our given information, we kind of ask, what does the given information tell us? Like, what can we get from this statement? Well, angle bisector means it cuts the angles in half, and so we might be able to say that for our angles, is that our angles here, our top angle, and our bottom angle must be congruent. And so that's the next thing we can say. We knew this because that's obviously the definition of an angle bisector. And now we try to say, what can this step tell us? Not too much. So what we can go ahead and say then is, where are we trying to go? We're trying to say the length of QS, the length of a point to a line, the length of a point to a line. If you remember, these are perpendicular lines, and so we need to talk about perpendicular lines. We need to talk about the perpendicular line SQ and the perpendicular line SR. And as you may have guessed, that is our next step, with the reasoning that that's the definition of the distance from a point to a line. Because these angles are perpendicular, we can say that these are, because these lines are perpendicular, we can say the angles are right angles. How do we know that? Well, we knew that because that's what the definition of perpendicular lines are. They form right angles. Because both angles are right angles, think about all right angles. They're always congruent. And so we're just going step by step, and step 4 can tell us that these angles must be congruent to each other. And although that seems pretty obvious to us, we do have a theorem, and that is the right angles theorem. And that just says that all right angles are congruent. Now if we look, if you notice, we have one set of angles that are congruent and another set of angles that are congruent. We can't go anywhere from here really unless we notice what we're trying to do. The end goal is, if you look, I see one triangle and two triangles. Maybe something we could do is use our previous knowledge, use the CP/CTC type stuff, and try to prove these triangles are congruent. If the triangles are congruent, then the individual parts, such as these segments, must be congruent. So why don't we do that? How do we prove triangles congruent? Through a shortcut. Side, 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 side angle, side, etc. But again, we have two angles. So think back all the way to the stuff that we can use with two angles. I see one relationship that we could use, and it's a relationship we use quite often. We know that the segment PS is congruent to the segment PS. It's the same line, and so we know that we use the reflexive property for something such as that. Now looking at this, we have an angle, and a side. That's a shortcut. The entire triangle PQS is congruent to the triangle PRS through angle, angle, side, as we just saw. Since the angles are congruent, the parts must be congruent. And lastly, if we have congruent parts through CP/CTC, congruency implies, well, what are we trying to find? The lengths are the same. That's what congruent means. And so by the definition of congruence, we have just proved what we wanted to. This proof, although 9 steps, was not too crazy once we noticed that we were using the past knowledge of the triangles, and we were looking for a shortcut dealing with them. We are done with the angle bisector theorem, and so now we have one more theorem dealing with the angle bisector theorem. It's fairly similar. This theorem here is the converse. Notice the word converse of the angle bisector theorem. What does the converse again mean? It means the opposite. And so keep that in mind when we're going to give this theorem. So what does this theorem say? It says if a point is on the interior of an angle and it's equidistant from the sides of an angle, then it is on the bisector. Remember, that's the exact opposite of the angle bisector. The angle bisector started off with if it's on the bisector, then it is equidistant. So it's completely flipped. Let's look at a diagram to see it. So we have an angle, as our theorem says. Now, we want a point on the interior. I'm just going to choose a point, let's say about right there. I chose a point on the interior. Now, what our theorem says is that if it's equidistant, meaning if we have a perpendicular line, again, because we're going from a point to a line, if the lengths are equidistant, meaning we have two congruent segments here, if it's equidistant from the sides, then it is on the bisector, meaning that we can draw a ray through our green point, and that this red ray must be the bisector. And so our converse tells us when we have a bisector, which is the exact opposite of our angle bisector theorem. Notice the difference. Now let's go look at when we'll actually use it. Let's finish off with 2 examples and see when we'll actually use this stuff. Our first problem gives us the following diagram and tells us that YW bisects the angle XYZ and the length of WZ is equal to 3.05. So we want to find the length of WX. So looking at this, because we're talking about a bisector, we could label our diagram as so. We're dealing with the bisector, and we're talking about WZ is equal to 3.05. So just putting in a 3.05 in here, we wonder how can we find out our blue length? How can we find WZ, WX? Well, looking at it, isn't W on the bisector? Since W is on the bisector, that means we can use our theorem 5-1-3, which is the angle bisector theorem. Using this theorem, we can see that the length WX is going to be equal to the length WZ. So we see that WX is equal to 3.05. That one wasn't too crazy. Let's look at one more. So looking at this, we see that it is the same diagram that we had before, but now different given that the measurement, we can go ahead and label our diagram, given that the measurement of angle WYZ is equal to 63 degrees, XW is equal to 5.7, and ZW is equal to 5.7. We want to find the measurement of XYZ, the big angle there. One thing that I notice is that W is in the interior of angle XYZ. What that means is that it's on the inside. It's on the inside of angle XYZ, which it is. Another thing that I notice is that two lines coming up to W are equal. They're equidistant, meaning that W is equidistant. Now, it couldn't just be two lines, not just two random lines. In particular, we have right angles. We have perpendicular lines. So what I notice again is that perpendicular lines going to W are congruent. With both of these knowledge, both things that I written in blue there, these lead us to say that we can use theorem 5-1-4. We can use the converse. Using the converse tells us that W is on the bisector. Okay, that's pretty cool. Why is that helpful? Well, because it's the bisector means that this ray that we have cuts our big angle in two. So if it cuts it in two, we know half of the angle. This other half must be 63 as well. That's why that's pretty cool, is that now we have a 63-degree angle because it's our bisector. And so therefore the measurement of angle XYZ is equal to 63 degrees. And so the key to both of these problems is determining, using all of our given information and determining, are we using the theorem or are we using the converse? And then once we start going, it's kind of self-explanatory. It leads itself.